Welcome to the next session of Strength of Materials. I am starting with the next topic of deflection of beams. From the chapter of bending stresses of beams, we have already derived the flexural formula, which was M by I is equal to E by R, which is sigma upon Y. M stands for the moment which is applied by this force at a particular distance. I is the moment of inertia. E is Young's modulus. What do I mean by this term radius? Suppose if I have a beam over here, I'll draw its FBD. This is my point A, point B. Since it is a hinge support, I'll draw one reaction VA and here VB. This is a load W that is acting. It could be at some point, say C. Now, if you look carefully, these two ends are going to push the body upwards, and at this point C, the body will be pushed in the downward direction, which means in all it is going to create something which is called as sagging effect. This is something we have already discussed in the previous chapter. This is something we have already discussed in the chapter of shear forces and bending moment. So this effect is called as sagging moment. Now the beam will bend something like this, but I have obviously drawn an exaggerated diagram. Please don't go by the amount of deflection that you see here. It's just a larger than life diagram for you. Now, what do I mean by this term R? R is actually the radius of this, like this is an arc if you can see. If I form this into a circle, obviously there will be some radius value R. So we say that this radius about which the bending is happening is a term R which you see here. Now, sigma is going to be the bending stress and y is the distance. Now, what is this distance? I'll explain a little bit in short. If you see over here, this is the beam which I have drawn. When I draw the FBD, I draw a straight line. This beam, which is a double line figure, becomes a single line. But actually the beam will bend something like this. It will be of the sort. Obviously the thickness will be there. So let's talk about the beam which is straight. There will be an axis which will be called as a neutral axis over here. Okay, this is obviously that beam AB. I have drawn over here which is called as neutral axis. Now, what is this neutral axis? We actually see this axis when you bend the beam. Okay, suppose if you see a sagging kind of effect, this will be that neutral axis which you are seeing over here. Now, neutral axis is nothing but the axis about which you don't see any effect of stresses. If you look at this figure, these layers are coming under compression effect and the layers below are going to be under the tension effect. But there will be just one layer at the center which will be subjected to equal amount of compression and tension, which means there will be zero amount of stress because they cancel out each other. So this layer is called as NA, which is the neutral layer or neutral axis. So y over here, if you see, y is nothing but the distance of either the compression side, the layer which is farthest from the center will be subjected to maximum compression. So we calculate over here yc, and here this distance is calculated as yt. So when I talk about the formula in terms of compression, I'll write here yc. If I write in terms of tension, I can write this as sigma c upon yc or sigma t upon yt. If I talk about the last layer, because the last layer is the one which is subjected to the maximum amount of either compression or tension. So these are all the terms of flexural formula. Now in this formula, if I divide it into two parts, if you look carefully, Mi is equal to E by R is equal to sigma upon Y. From this, if I cut out M by I is equal to sigma upon Y, this is nothing but the strength criteria. When I say M by I is equal to E by R, this much portion is called as rigidity criteria. When an engineer is supposed to design a beam which is subjected to some amount of load and some loading conditions, supports over here, and at that stage he has to design the beam not only for the strength criteria, which means not only for the stress that will be subjected to the beam, he or she also has to calculate the dimensions for the rigidity criteria, which means there will be a particular amount of stiffness in the beam for the amount of deflection to happen. It may deflect, it may not deflect. If it deflects, it could lead to problems like cracks in the plaster of a beam or a column. So obviously the designer has to design for the strength as well as for the rigidity criteria, which means how long it is going to withstand before it fails is important for us. So this chapter, deflection of beams, basically is going to deal with only this part of the formula, which is m by I is equal to E by R. This part of the formula above of strength criteria will be dealt in the chapter bending stresses in beams. So these are the two chapters which combine, and that's how you can use the flexural formula. But here I am going to only use the rigidity criteria part. Next I'll talk about the moment curvature relationship. As I have told you that any beam is going to bend. It could be in a sagging kind of effect or it could be a hogging kind of effect, any one of the two. In this case, there is obviously a radius, as I told you, r, about which the beam bends. So this equation I've written over here is for the radius r. Now you would ask me what are these other terms. Now let me draw a small beam, say A and B. Say it is subjected to some amount of load W. So this beam is going to bend something like this because of the load. So this will be my point B and this is my point A. This will become B dash as of now. So obviously there will be some amount of slope. This is called as theta. Now this direction is going to be y and this direction is x. So at a particular point on this beam, suppose if I want to calculate the deflection, it will be some distance x. And this point will obviously not be a point, it will be obviously some amount of a distance, say dl, a small length L. So when I calculate the slope over here, and that is something which I use for calculating the radius of the circle made by the arc which is formed when there is a deflection happening. Now there is an equation for this which I have taken. I am not going into the derivation part. So with this I am going to just use the formula. The equation which we just saw is m by I is equal to E by R. So instead of R I am going to use this equation. So this would be E into d square y by dx square. So I can just write on the formula m is equal to E into I. The I will get multiplied over here, d square y by dx square. So this equation is called as a moment curvature relationship. This equation is something which you use as a base moment equation in studying about deflection of beams. There are three types of studies which are possible. As you can see, this is a beam. I have already told you that we are studying basic SOM. We are studying about the linear part only. So when I say that I want to calculate the deflection of the entire beam, or if I want to calculate the deflection at a particular point, there is a very simple method that I always use, which is choose a very small length, calculate the value of deflection at that point, integrate and calculate for the entire beam. So that's a very simple logic that we use. Now there are various methods, as I'm telling you, for calculating these deflection. I would just name some of them for you. One is double integration method, one is called as a superposition method, and third one is called as Macaulay's method. Now I am going to use Macaulay's method for solving further in this chapter. So we will start with this equation and then we are going to calculate the other terms. I am going to discuss about that in a while. We will see some assumptions which are made when you study deflection of beams. The first one is the deflections and slopes are small in this kind of a beam. The beam is very long when compared to its cross-sectional dimensions, that is, the length will be quite greater than its width and its depth. If you have a beam here, as you can see, so this is the length L, width B and depth D. As you can see, this L is quite larger as compared to B and D. Third one, the deflection due to the shear force is negligible. This is very, very important. When compared to the deflection due to moment, we are going to mainly study about the moment which is causing the deflection on the beam. We are not talking about a small deflection due to a shear force, because that is considered negligible in the kind of study that we are doing. The value of E and I will remain constant for a given interval along the length of the beam. Now this is again a very, very important assumption. When I say the value of E is going to remain constant, it means the material is going to be isotropic, which means if this is my beam along the three axes, say if this is one axis, this is the other axis, and this is the third axis. So if I have three axes, Y, say Z and X, along all these axes my value of E is going to remain same. Isotropic is the term used. When I say I remains constant over some interval of length of the beam, it means that suppose if I talk about a particular section here and I talk about a section little at a distance, if there is a gap between these two planes or two sections on the beam, the value of I will remain constant, which means because of this deflection there is no change in the value of B and D, which means the dimensions of the beam will not change altogether, although there is a small deflection happening. So that's a clear meaning of this assumption. Okay, having spoken about the assumptions, I will just brief you about the sign convention that we are going to use. So when I talk about the sign convention, any force which will go in the upward direction will be considered positive, and any force going downward will be considered negative. Any force which is going towards the right will be measured as positive, and any force going towards the left will be negative. A moment which will be clockwise will be considered positive. So these are some of the sign conventions that I am going to use. Now let's start. Some other useful equations we need to discuss. We will first start with deflection, because the name of the chapter is deflection. So for deflection, I am going to use the term y. When I talk about slope, I'll be using the term theta, which will be dy by dx, which is the slope. Next, I'll be talking about the term moment. When I say moment, the equation is something which I have just written, ei d square y by dx square. This is the moment curvature relationship. Now, if I talk about a particular term which is shear force, if you recollect shear force and bending moment chapter, there I have actually derived an equation for F and M. F was dm by dx. Here if I substitute the value of M, E and I being constant, I will only derivate this term d square y by dx square. The third derivative of it is d cube y by dx cube. Next we will talk about a term intensity of load. If you recollect, the term W was df by dx. There was a negative sign. Here I am not using the negative sign. So the term F over here is ei d cube y by dx cube. Ei is again constant. So when I calculate the derivative, I'll be calculating for this much term only. So this becomes the fourth power of the derivative term. So these are some of the equations that I have written, and these are the equations which need to be studied, because you will see an interesting relation here. When you walk upwards, you will see that each term has been integrated. If you integrate d square y by dx square, you will get dy by dx. So here when I walk up, what I do is I integrate. Similarly, when I walk further up, I am going to integrate. So integrating once the moment equation, I get the slope equation. Integrating the slope equation, again I get the deflection equation. Now suppose if I derivate the equation, if I derivate this equation, I get the shear force equation and the load equation. So these are some interesting equations which we need to know. and we will be using a set of these three equations mainly. So with this I end this session. This was a very basic briefing of the chapter. In the next session we will discuss in depth about Macaulay's method, and we will start with the numericals after that. So I hope you have understood this session. See you in the next session. Thank you.